The story of gravitational theory begins long before Newton or Einstein. Ancient astronomers, such as the Babylonians, Greeks, and later Johannes Kepler, developed methods to predict celestial movements with incredible accuracy, despite having no direct way of observing all the bodies involved. They knew there were unobservable forces at play. By analyzing the motions of visible planets and stars, they deduced the existence of unseen objects, understanding that celestial systems operated as balanced, interconnected wholes. This ancient insight was critical. They recognized that bodies in the heavens were part of closed gravitational systems, bound by unseen forces that stabilized their orbits and dictated their movements. This historical approach laid the groundwork for our modern understanding of gravity, but it also inspires a deeper question. What if those early astronomers were intuitively grasping something beyond a simple binary interaction between two objects? What if the systems they were observing and predicting were inherently more complex and triadic? Our exploration of triadic gravity represents a significant shift in how we understand gravitational systems. Traditionally, gravity has been viewed as a pairwise binary interaction between two masses, such as the Earth and the Moon, or the Sun and its planets. However, we propose a new framework that moves beyond this binary thinking. Triadic gravitational systems, where stable interactions occur between three bodies or systems of bodies, provide a more accurate and comprehensive model for understanding the dynamics of galaxies, clusters, and even the larger structure of the universe. Our theory of triadic gravitational systems builds on the wisdom of the ancients, just as those early astronomers inferred unseen planets from the behavior of observable ones. We propose that gravitational systems are not simply pairwise interactions, but rather self-balancing triads of objects. These triads, or groups of three, provide the stability and cohesion needed to explain the large-scale structure of the universe without invoking exotic solutions like dark matter. In doing so, we aim to refine and expand our understanding of gravity by returning to the core insight that gravitational balance comes from interconnected systems. In this presentation, we will explore the foundations of this triadic gravitational model, its implications for localized gravitational influence, and the role of nested triads in the larger cosmic structure. Let's begin by laying out the core idea that moves us from the flaws of the binary model into the triadic realm. Our starting point lies in recognizing the limitations of the binary model. In most classical and modern approaches, gravity is described as a binary force. Two objects attract each other based on their masses and the distance between them. Newton's law of gravitation and Einstein's general relativity both model gravity as arising between two masses, which works for small systems like Earth and the Moon or the Sun and a planet. However, cosmological systems are not isolated. Galaxies, clusters, and even planetary systems exist in complex networks of influences. A binary model cannot fully capture the emergent, systemic behavior of these large structures. In a binary system, the forces at play are linear and relatively straightforward. Two objects pull on each other according to their masses and the distance between them. Triads, or systems of three, naturally lend themselves to stability in complex environments. A triad is more balanced and stable than a binary system because it introduces an extra degree of constraint and feedback, allowing the three masses to distribute forces more evenly. In a binary system, you only get a linear pull between two objects. But in a triad, each object interacts with the other two, leading to a more robust, self-balancing system. Ancient astronomers recognized that celestial bodies moved in patterns of balance, and this balance allowed them to predict not only the existence of unseen planets, but their motion. Reductionist binary interpretations of gravitational forces would never have enabled this. The ancients were able to restrict the number of gravitational variables to consider. Thus, we argue that gravitational stability arises from triads of interacting bodies rather than simple pairs. This triadic system creates a self-balancing configuration where the forces of gravity are more evenly distributed, resulting in greater stability across complex environments. Examples of this can be seen where multiple planets or stars interact gravitationally. Instead of thinking of bodies interacting in pairs, they exist in triads or higher-order groupings, where the system as a whole stabilizes because each body influences the others. Similarly, in galactic clusters, we see groups of galaxies exerting gravitational influences on one another, forming structures far more stable than binary interactions could predict. These systems are self-balancing because the triadic interactions maintain equilibrium. The next crucial concept in our theory is the localized nature of triadic gravitational interactions. Building on the ancient concept of closed systems, we propose that gravity does not act universally the same in all contexts, but is instead determined by the local configuration of interacting bodies. In other words, the gravitational constant is not a fixed number throughout the universe, but may vary based on the specific mass distributions within triadic systems. Here we draw from Dennis Sciama's framework of gravitational influence, which is often discussed in terms of Mach's principle, where inertia and gravitational forces are influenced by the entire universe's mass distribution. However, we propose that gravitational effects are localized within triadic systems of objects, rather than being determined by the mass of the entire universe. Each triad, comprising 3 interacting bodies, forms its own localized gravitational field with the gravitational coefficient specific to the triad. This gravitational coefficient is not a universal constant in the traditional sense, but is instead dynamically adjusted based on the distribution and mass of the objects within the triad. Triads form from the 3 closest objects large enough to exert gravitational force, creating a field which exerts a gravitational influence focused on those 3 bodies. This localized gravitational coefficient ensures that the forces are strong and coherent within the triad, rather than being diluted by the vast emptiness of space. This idea of localized gravity is not limited to single triads, but extends to nested systems, where smaller triadic structures are embedded within larger ones. Planets and moons may transition from one local group to another throughout their orbits, creating wobble effects like the Earth's precession. Groups of triads form larger triads which orbit the Sun as a whole. This solar system triad, in turn, interacts with and forms a part of a larger triadic structure involving nearby stars and their systems, and this pattern continues up to the scale of galaxies and galactic clusters. Each layer of the nested system maintains its gravitational integrity. A triadic gravitational field acts on other components of the triad as a whole, regardless of how nested and large those components have become, providing far more integrity over vast empty spaces than does a binary model. This provides a logical explanation why galaxies, for example, retain their structure far better than expected, without requiring exotic explanations such as dark matter. This model also provides a pathway to address the galactic rotation problem, where the outer regions of galaxies rotate faster than expected based on visible matter. Traditionally, this has been explained by invoking dark matter, an unseen substance that provides additional mass and gravitational pull. However, in our triadic model, the stability of galaxies can be explained by the localized gravitational fields within nested triadic systems. Each triad contributes to the galaxy's overall gravitational integrity, preventing the need for unseen mass to account for the observed dynamics. One of the most profound implications of the triadic model is its ability to explain emergent gravitational behavior. Rather than viewing gravity as a force between isolated pairs of objects, we propose that gravitational effects emerge from the interaction of triads within a nested hierarchy. This framework helps us understand why cosmic structures behave coherently on large scales. In the traditional binary model, gravitational forces are linear, acting directly between 2 masses. But in the triadic model, each body in a triad influences the other 2, creating a more complex, multi-directional force network. These interactions generate emergent properties, where the collective behavior of the triad stabilizes the system. The emergent stability seen in galaxies and clusters results from the interplay of triads. Each triad reaches a point of dynamic equilibrium where the gravitational forces balance and reinforce each other, leading to a stable system that behaves coherently at larger scales. This explains why we observe galaxies and clusters behaving as unified entities, even though they are composed of countless individual stars and objects. Returning to the insight of ancient astronomers, the predictive power of the triadic model becomes clear. Just as those early astronomers inferred the existence of unseen planets by observing the motions of visible ones, formalizing the mathematics of the triadic model will allow us to predict unseen gravitational influences by analyzing the behavior of observable objects within a triad. Consider a system where two celestial bodies exhibit gravitational behavior that cannot be explained by their visible masses alone. By applying the triadic model, we can infer that a third unseen body may be exerting gravitational influence, stabilizing the system. This method mirrors the way ancient astronomers deduced the existence of planets without directly observing them, using patterns of balance to reveal the presence of hidden forces. The triadic model's predictive power also extends to larger cosmological questions such as the nature of dark matter and dark energy. Instead of positing the existence of exotic forms of matter and energy, we can look at the universe as a nested series of triadic interactions. This could offer explanations for the strange rotation curves of galaxies or the accelerated expansion of the universe as emergent properties of gravitational systems operating on a triadic hierarchical basis. The practical implication of improved calculability of complex gravitational forces offers many benefits. It promises significant improvements in space navigation by accounting for the interdependent gravitational forces between three bodies, leading to more precise orbital calculations and efficient mission planning. This would enhance trajectory accuracy for long-duration missions and optimize slingshot maneuvers around planets like Jupiter, ultimately reducing fuel consumption and increasing mission success rates. Incorporating triadic gravitational interactions can vastly improve satellite stability and collision avoidance by better predicting how Earth's satellites interact with the gravitational influences of the Earth, Moon, and Sun. This is particularly useful for satellites in crowded orbital environments and for exploiting Lagrange points, where the interaction of multiple gravitational forces creates stable regions ideal for satellite deployment. Perhaps most importantly, the triadic model promises more accurate prediction of near-Earth object trajectories, enhancing our ability to track and prevent asteroid collisions. By understanding the gravitational influence of multiple bodies on an asteroid's path, we can improve the precision of impact predictions and deflection strategies, increasing the effectiveness of planetary defense systems. Any of these potential benefits should provide motivation for anyone seeking to confirm this theory with astronomical data. The triadic gravitational model offers a revolutionary way of understanding the cosmos, moving beyond the limitations of binary gravitational interactions. By focusing on triadic systems, we gain a more accurate view of gravitational stability, localized gravitational fields, and emergent cosmic behaviors. The nesting of triads within larger systems ensures that gravitational interactions remain coherent across scales, offering explanations for galactic cohesion, cosmic expansion, and the structure of the universe itself. This model challenges traditional views by proposing that gravity is an emergent property of triadic systems and that the universe organizes itself through these nested triads rather than relying on pairwise forces. The triadic gravitational model offers a profound shift in how we understand and predict gravitational interactions. By proposing that gravitational stability arises from triads of three closest bodies, which constantly shift and reorganize as the distances between objects change. This model provides a more dynamic and realistic framework for analyzing both small-scale and cosmic gravitational systems. To fully explore and validate this theory, we must go beyond abstract concepts and engage in direct empirical analysis. At its core, our method is simple yet powerful. Identify the three closest objects in any gravitational system group them as a triad, and calculate the gravitational forces between them using both the traditional Newtonian approach and our proposed locally calculated gravitational constant, based on the specific mass and distance configurations within the triad. The next step is to apply it to real-world celestial observations. By selecting well-studied systems, such as planetary orbits, moon-planet interactions, or even the motion of stars in galaxies, researchers can calculate the gravitational forces within triads, then compare these predictions to observed behavior. If our model holds, the triadic calculations should yield better alignment with actual orbital paths and motion stability than current binary models, especially in complex environments like multi-body systems or galactic clusters. Our triadic gravitational model is designed to be intuitive, accessible, and open to exploration by anyone with a curiosity about the cosmos, not just professional scientists and astronomers. Whether you're a dedicated backyard researcher, an amateur astronomer, or someone passionate about science, you can contribute to exploring and validating this theory. The concept is straightforward. Triads form dynamically between the three closest objects in any system, shifting as those objects move. To apply this model in your own research, all you need is basic knowledge of gravitational calculations, an understanding of distances between objects, and access to observable celestial bodies, whether you're studying the moon, planets, or stars. Simply identify a triad. Look for any group of three nearby objects, such as planets, moons, or stars, within a defined region of space. Calculate the gravitational forces. Using the traditional formula for gravity based on the mass and distance of the three bodies within your triad, we can then compare the calculations with our proposed local gravitational constant using a modification of Siama's formula. Three objects in space, A, B, and C, form a geometrical shape. Generally, 3 points in space form a triangular or ellipsoidal configuration based on their relative positions. The radii can be thought of as the semi-major and semi-minor axes of an ellipsoid formed by the triad. By averaging the two radii, we get an effective distance between the objects in the triadic system. This is a reasonable way to simplify the geometric complexity into a more manageable form for calculating the local gravitational constant, radius 1 plus radius 2 over 2. This averaged radius provides a scalar measure of the relative distances within the triadic system, capturing the general size of the ellipsoid formed by the objects. To express the local gravitational coefficient, divide this averaged radius by the total mass of the triadic system. Then compare predictions with observations. Whether you're using a telescope, tracking data from space agencies, or analyzing available data sets, we can compare the predicted behavior of objects in triads with real-world observations. Modern astronomy has made available data that took the ancients millennia to accumulate. The beauty of this approach is that it doesn't require a massive lab or complex equipment, just curiosity, a basic understanding of physics, and a desire to explore the universe from your own perspective. The method is simple and the potential rewards are vast. By comparing your triadic gravitational calculations with actual data, you might help reveal patterns or better predict orbital dynamics that traditional models miss. You don't need to be a professional astronomer to make meaningful contributions. You can start small, observing how the Earth, Moon, and Sun interact, or investigating planetary moons, and as you grow more comfortable with the model, you can expand to larger systems like star clusters or even galaxies. Your independent work could provide valuable insights, helping to validate the triadic model and showing how accessible and powerful this new way of understanding gravity truly is. This is a model for all explorers. So whether you're working from your backyard with a telescope or from a computer analyzing data, you have the power to contribute to our understanding of the cosmos. We invite you to engage with this theory, test it in your own way, and help expand the collective knowledge of how our universe operates on both small and grand scales. Together, we can open up new possibilities for how we see and understand the forces that shape our world and beyond.